Hello and welcome to this presentation. My name is Lukasz Chodyła and I'm pleased to present the results of my team's work at this conference. The co-leading designer of this project was Adam Zientek, and the project itself, co-financed by the European Regional Development Fund, was carried out by the Platforma Biznesu company located in Poland. The subject of our work was the development of a multi-component platform allowing remote application launching, including screen space, partitioning, and manageability for Linux-based systems. Today I'm going to start by giving a bit of a background on our story, tell you what drove us to conduct the research, what our objectives were, and then briefly discuss the design of the proposed solution. The company has been operating since 2012 and owns many products in the field of digital signage, queuing systems, data processing, or interactive entertainment. When implementing our products, we look for opportunities to innovate. And in the past, our offer included a content management system with which we competed in the market in a traditional way. Traditional here usually means a device with a single application serving full screen content. Content division, if any, is usually handled by this singular application. Changing the type of the content, for example, from weather forecast to a video or to a game, means switching applications or mixing domain-specific features and general-purpose features in one application using the same technology. Another issue that arises from the previous point is the lack of flexibility in extending the system after its installation. This is especially interesting from the business owner or product owner's perspective. The content presented by remote devices needs to be updated, which concerns not only the information itself, but also the presentation method. Any customization involves hiring the original software provider or following strict guidelines regarding the API or technology being used. Outsourcing the application the application development would typically require alternating or updating the current software. On the other hand, using existing well-known accessible applications, especially simultaneously on a shared screen, could reduce expansion costs, but this is not common in current market solutions. Also, the content update process can be improved by more efficient bandwidth and storage management. The software update process can be streamlined and secured, especially with multiple applications sharing same dependencies. Okay, our objective. The main objective is multi-application remote management. It means running different applications, providing different functionalities without being limited to a specific technology, such as programming language, set of libraries, or framework, or else. This is quite a bit conceptual change, because there are frameworks for just launching applications, just running processes, but we're breaking the traditional pattern from an application serving content to the design of an entire system serving applications. This implies mapping the visual layer onto physical screens. In other words, we wanted to allow multiple full screen applications to be run at the same time on a partition screens. There is also the matter of hardware acceleration and hardware access, because we never wanted to use operating system virtualization in the process, so we wanted to enable all running applications to access hardware resources such as GPU or GPIO. And besides that, we were focused on independent updates and process separation, reliable software upgrades, and zero operation version switching that I will be talking about in a minute. Okay. The project was launched in 2017. To this day, the key objectives have not changed. There are a few solutions on the market that address individual problems we have identified, but there is no comprehensive solution such as we have developed over the last 5 years. The change of approach from an application serving content to a system serving applications generates many new challenges such as maintenance, updating, security, and convenience of use. However, it also opens up a huge field for innovation and research. I will be presenting a collective of several components, each of which has been or is the subject of separate research. This presentation is intended to give a general perspective of what the components are and how they work together. We mainly examined the Xorg implementation, X Windows Server, with a number of window managers, including our own extensions, and the Wayland server with our implementation of the Desktop Composer. Among others, technologies such as Qt4, Qt5, GTK, SDL, Python tag have been tested to determine typical working patterns and also metadata useful during the process. Our work mostly results in a set of methods solving given classes of problems and in a collection of constraints drawn during experiments. For example, although studying the papers and articles may point to Wayland as a modern and ideal solution, practical experiments have shown a lack of readiness for production applications, at least in our case, some difficulties in portability, and lack of full backward compatibility with applications written for Xorg server, even when used with Xwayland extension. All this combined in the implementations of the components working together creates a system that meets our original requirements. Okay, here's a very simplistic block diagram with abstraction layers or communication modules cut out. I'm going to briefly cover the three main parts here. First part is the layer composer. The layer composer is started at the system boot stage. It assembles the system image at the file system level, so without any file operation, without moving or copying files. It can run tests and it decides how to save or how to write files, whether it will be RAM or persistent memory. These are the layers we send when we are updating the software or installing new applications. All layers except the top one are read-only, so any damage can be easily undone. Also, with overlay FS, which we're using in our implementation, it's also possible for one layer to make a file from a lower layer disappear, and ultimately it will look like the file has been deleted. This is actually a broad scope and the subject of separate ongoing research. The result will be published and the implementation will be released as an open source software. If you are interested in this aspect in particular, please feel free to contact us. Next, we have the system service, of which the main components are the process execution and and process tracking module, and the window mapping module. In short, here we use inter-process communication to handle window drawing events and create virtual displays for full screen applications to trick them a bit and control screen partitioning. At runtime, a map identifying processes, forked processes, because process can fork itself after being launched, is built to connect the signals from the windows to the original processes. In addition, which is not visible on this diagram, there is an interpreter and executor of special rules defined both at the time of application installation and content update. These rules are often empty, but one of the goals was to be able to outsource application development without imposing strict standards. So in this case, even if someone implements the application in some bizarre way, far from what we consider a standard, such a rule can, for example, match an expression from the window title with a process ID. So we know where it should be drawn on the screen. In this way, we don't have to re-implement the way different applications are handled. The last part is the application data cache management component. And the issue here is frequent uploading of files, often the same and large files used by applications at long intervals. For example, videos with advertisements or exhibition promotions interleaved with something else like news of the day. Traditionally, we were using first in, first out model and deleting the oldest file, but it was obvious we could do better. So what this module does is firstly collect information about files, and this is not a separate application, it's a file system. So there's no periodical checks or any watchdog. It's file system doing it on its own. So what it does is, among other things, it knows when the file was opened, whether it was changed or just read, and for how long it stayed open. Then when new data arrives, each resource is evaluated according to a preset formula, and when the quota is exceeded, the resource with the lowest score is removed. So the evaluation formula depends on the use case, and it can be, for example, the size of a file divided by the total time it's been in use. Then large files are preferred, but a small file being in use all the time can outrun them. The main advantage of this approach is that it's independent of how the file ended up on disk. It could be uploaded to an HTTP server, it could be synced from the cloud, or it could be copied from an USB drive. Okay, current state. Over the past few years, many of the key components have been implemented where we previously used a traditional approach. We've seen significant productivity gains while reducing costs, and the system as a whole or in selected parts can be used in single or multi-device systems based on Linux. And as we believe, the proposed solution can also benefit schools and public facilities, especially layer updates and the file system level resilience. A student may delete any system file experimenting, as everything will be undone upon reboot, or stored as a separate layer for example, teachers' review. Okay, so that's where we are today. Thank you for your attention, and I encourage anyone interested in working with us to contact us at the address now visible on the screen. So thank you.